So we're going to talk about diffusion model today. I guess probably some of you have seen my message in ad. So we changed the order a little bit just because this is very close to the EM algorithms that Chris talked about last week. And I think it makes sense to discuss it early. So diffusion model are generative models for mostly images these days. You can do it for videos, for robotics applications. Actually, most of VLA, the vision language action model, are using diffusion models for generating the actions. So, so they are kind of like quite different from a typical large language model, to some degree. So, the training of the models requires some variational inference, or the EM algorithm. So, and we'll mostly use the image as the target application. So basically think of this task is that you have a lot of natural images, and your task is to generate a clean, realistic image that is similar to the distribution of the images you are given with. So, for example, you can say, I'm going to generate, just I'm giving image data set, and I'm going to generate images that are very similar to that. Similar in the sense that they are from the same distribution, very realistic, but not the same distribution. And this has been studied for quite a while, this kind of like generative models for images. I think before this, people are using GANs and variational autoencoders. And now diffusion model is the predominant approach. I think it's much better than both GANs and variational autoencoders. And that's why we don't teach GANs and variational autoencoders anymore. I think I still have some lecture notes in the notes about variational autoencoders. If you're interested, you can read them. But now the default way is doing diffusion models. And also it has applications in videos and robotics. So that's why this is and by the way, actually people have been using this for languages as well. I think Professor Stefan Ehrman, so he actually has a few papers on this, and he has some startup, I think, trying to make this large language models much faster using diffusion models. One of the benefits of diffusion model is that it can generate in parallel in some sense, so that your inference time might be faster than autoregressive model. I know we haven't talked about autoregressive model yet, but anyway, these are just the broader backgrounds. You don't have to understand every details here. Anyway, so to zoom in and to make it narrow, I think the goal we have today is just that abstractly speaking, you have some kind of like distribution of data, let's say P data. You have some empirical samples from P data, and you want to come up with a model such that you can generate from your model if you take the inference of the model, then you're going to generate from this distribution. So that's kind of like the task. So you want to generate data. You want to be able to generate from this distribution, and you're given empirical data from this distribution. Now, think of this distribution as the distribution of natural images, for example. I think the notation we have is that we always use x0 as a variable that is sampled from P data in some sense. So if I write this, I mean like I generate some empirical say realistic, images. Let's say x0 is this data distributions in RD. This is just to set up some notation. The core idea of this diffusion process is that during the inference time, when you are generating, what you are going to do is that you're going to start with a noise. You're going to start with a noise, something called XT. Let's say this is a white noise. Imagine you have an image with all the RGB are purely random. And then you're going to apply some model, backward, and to generate XT minus 1, and you can generate XT minus 2, so on and so forth. And then eventually you generate some X0. And this model, let's call it P theta. Say this is the model between P theta XT minus 1 given XT. And then you apply the model again, and XT minus 1 given XT minus 1. So it's a Markov chain when you're applying this, and eventually you apply P theta x0 given x1. Theta is a parameter you're going to learn. It's often a neural network with some structure, oftentimes some kind of like MLP. And then you do this, in this way. So basically the goal is to learn some theta such that you can generating a sequence of images and you have a really realistic image. So here, this is a noise. I don't have I'm using the blackboard, so I cannot really draw an image here, but this is a pure noise, and this is a real image. And in this sequence, you are getting more and more kind of like a fine-grained, images, right? So this is like a very blurry, and then you get a less blurry, and you start to see some kind of like contours of the objects, and then eventually it's a very clean, sharp image. So it's kind of like you are denoising, over time to denoise it into a, clean image. So that's the high-level idea, the very, very high-level idea. So the question is, how do we learn this? Okay. So, and the main technical approach is called this diffusion process. So, the way to do it is that you say, I'm going to model, in the training, I'm going to model, kind of like a noising process from the clean images to the noise image. And then I'm trying to learn the reverse function in some sense. So basically, you'll see that we're going to have a model where you have a model Q that generates x1 given x0, and you do the same thing here, and you do a Q xt minus 1 given xt minus 2, and then Q of xt given xt minus 1. And so you define some kind of like a so-called kind of noising process, and then you try to learn the reconstruction in some sense. And actually very interestingly, so the noising process is very, it's just adding Gaussian noise. So this, noising process Q is just adding Gaussian noise. I'm going to define exactly how you add Gaussian noise, but roughly speaking, you just add more noise to each of your images, and you have you can start from a real image to get to the noise image by keep adding noise. And then you try to learn how to reconstruct, this process. And now let's discuss exactly how you add noise. So the way to add noise is that, you can write it in different ways, but one way to write it is that you say x1 is equals to, 1 minus beta 1 x0 plus square root beta 1 epsilon 1. So and where, say, epsilon 1 is standard Gaussian, and beta is a scalar, which is often close to, 0. So it's a scalar between 1 and 0. So basically what you do is you say let's say beta is actually relatively small, like close to 0, maybe like 1e minus 2, 1e minus 4. So basically you shrink the original image, the clean image by a little bit, slightly, and then you add a little bit noise to it. So basically the scale here is the noise scale is very small in one step, and you shrink the original image. So basically when you do this, you only make the original image a little bit blurry, because most of the signal are still here, and you add a little bit of noise. And then you can do it next time. So you say x2 is equals to 1 minus beta 2, x1 plus square root beta 2 epsilon 2, where epsilon 2 is another IID draw from standard normal Gaussian, and beta 2 is also chosen between 0 and 1. So I think exactly how you choose beta I'm not going to discuss in this lecture, because there are many different ways to choose the beta. But generally speaking, beta is a pretty small number. And you do this, iteratively until you get xt, which is equals to 1 minus beta t xt minus 1 plus square root beta t epsilon t. And actually epsilon, for every t, epsilon t is IID from standard normal distribution. So, and you may wonder why I'm choosing these two coefficients here like this way, right? This is because, in some sense, beta I is the noise, the variance of the noise you are adding, right? So wait. It's not about the force. Something is getting stuck. Do I need to use this? I guess if I don't use this, then this one is not movable, so I cannot. Yeah, I think I have to use it. Otherwise, I'm losing one board. Okay, anyway. So, okay, so why, I think maybe some of you may wonder why you are choosing this, kind of like choosing the coefficients in this way. I think the reason is that if you think about the covariance of xt plus 1, so this is the covariance of square root 1 minus beta t xt plus square root beta t epsilon t. And because these are independent, the noise is independent, is an independent Gaussian noise. So, the covariance is additive. So you have the covariance of and then the covariance is actually a quadratic function, right? It's a you can put this constant out and you get the square of it, so you get 1 minus beta t covariance of xt plus beta t covariance of epsilon t, which is 1. But maybe let's just write covariance of epsilon t, which is identity. So in some sense, I guess maybe I just write this. So basically what I'm saying is that you are linearly interpolating. It's a linear combination of the previous covariance and identity. So maybe let's say, okay, of course it depends on so basically maybe the easiest way to think about this is that if the covariance of x1, x0 is identity, then the covariance of all xt is identity. Because you are not really changing anything, right? You are just maintaining the covariance. Every time you plug in identity here, you get identity out. So let's say suppose you normalize your data at the beginning so that the covariance is identity, then you are keeping the identity forever. So you are not changing the scale, you are just mixing in more noise without changing the scale. Of course, maybe in some practical cases, the covariance at the beginning is not identity because it's not like you can have correlations, zero correlation between all the coordinates. But even in those cases, you are just linearly interpolating, right? For example, you say the covariance of x0 is here and the identity is here. Then you are just moving along this line. So the first time your covariance of x1 is going to be here. The next time you're going to get closer and eventually you're going to converge to identity. And you are maintaining the overall scale in some sense, right? Like for example, if you look at trace, or some of the other scalar measurements, you are not changing. Like you are basically staying on the same kind of like, order because you never add more mass. The sum of these two coefficients is 1. So you're always between, along this line. So you never change the scale dramatically. So, right. So, and you can also see this, and how far you are moving from here to identity. I guess, also how far you are, I think actually, and by the way, this is covariance, but you can also talk about distribution. Eventually, you can also argue that the distribution of xt will just be Gaussian when t goes to infinity. Not only the covariance converges to identity, but also the diffusion itself will converge to just the standard normal Gaussian. I think you can see that from some kind of like derivations, to unroll this process. So what you can do is you can say let alpha t is equals to 1 minus beta t. This is just for convenience. So alpha t is going to be close to 1. And then you can unroll this quantity. You can say for every xt, you have the first thing is alpha t xt minus 1 plus beta t epsilon t. This is by definition. And then you can plug in the definition of xt minus 1, which is alpha t minus 1 xt minus 2 plus beta t epsilon t minus 1 and plus beta t epsilon t. And then you can plug in the definition of xt minus 1 again, and you can keep doing this. And eventually, if you roll out everything, then you're gonna get something like this: alpha t minus 1 up to alpha 1 times x0 plus this is a pretty complex formula, but actually it's not that complicated to guess if you do a little bit more kind of like a. So, the formula looks very complicated, but actually if you expand this, you kind of see the beginning of it, right? So alpha t minus 1 times xt minus 2 plus alpha t beta t epsilon t minus 1 plus beta t epsilon t minus epsilon t. So basically you always get a, no matter how many times you roll out, you always have a one term which is something times x plus a bunch of epsilons, some linear combination of epsilons. So linear combination of the epsilons will eventually go into this, which is complex, but no. If you do a few times, you're going to see the pattern, and it's actually exactly this. This is a linear combination of the epsilons with some coefficients, which I wrote at the end, but this is just a constant scalar of times epsilon. And then, the first term will be something times x, and the index for x will go from t to t minus 1, t minus 2, eventually to x0. So then you get some constant times x0. So, and people actually, tries to introduce a notation to simplify this. Let's say, suppose you define alpha bar t to be alpha t times alpha t minus 1 times alpha 1 until alpha 1. Then this equation will continue. You can write it as alpha t bar x0 plus, actually if you simplify everything, you find this is equals to 1 minus alpha t bar epsilon, let's say epsilon, where epsilon is from standard normal. So I guess, it's probably not entirely clear how this simplifies to this, right? But actually it's not that magical, because, so this goes to this, right? That's just by definition, right? Why the second term becomes this one. So first of all, this is a linear combination of standard normal Gaussian. So it's going to be another standard normal Gaussian. All the epsilon i's are IID. So no matter how many linear combinations you do, you're going to still get standard normal times a scalar. So the only question is why this scalar is this one, right? And actually, if you think about this, you'll figure out that actual scalar can only be that one, because suppose you believe that x0 has identical variance, then we argue that everything should have identical variance, right? So suppose x0 has identical variance, then everything will be stationary and covariance will be the same. And that's why the only scalar that can make this identical variance is this scalar, so that you can make the sum of the squares of this to be 1. So in some sense, it's not surprising, it just equals to this. No, because this is the standard deviation in front of the Gaussian. If you look at the covariance, it's the square of this.
I just had a question about that part. We just got rid of the under root in the alpha t and beta t when we designed the equation xt equal to alpha t x2 minus 1 plus beta t. We just got rid of the under root.
Sorry. Maybe can you repeat the question? Maybe I didn't get it. Sorry.
Like how we have, the way that you have points where you have the under root, and that's because of the covariant variance thing. But then when you defined alpha is nothing but minus beta, you did not have.
Oh, I see.
So why is that?
Sorry. Let me think about this. I think this is my problem. Sorry, my bad. I'm missing some square root here. Let me see what I'm missing here. Sorry. Let me think. I guess this is my, you are totally right. So, I think it's just that I'm having some typos somewhere. I think I just have a typo here. I have Yes, so I think I have a, sorry, you're right. I'm missing square root for everything. So alpha t is equal to 1 minus beta t, and this everything here has a square root. Just square root, square root. And then everything is right, except this is also square root. Sorry, maybe that's, yeah. Thanks.
Find alpha t bar as the square root of.
I think alpha t bar is the product.
Oh.
And then you have a square root here.
Okay.
Yeah. So yeah, and this is the reason why there are so many square root here is just because I think in the original paper that does this, they use this because, in some sense, if you ask a mathematician, they tend to use, like they wouldn't necessarily write this. They would probably use so here you are using beta 1 as the variance and square root beta 1 as the standard deviation. Typically in mathematical notations, like people like to use something square as the variance for the Gaussian, like beta 1 square, for example, and then you would write beta 1 here as opposed to square root beta 1. But I think in this area, people have converged to this notation. So everything, you have to follow this in some sense. Yeah. I found one paper that didn't use this, but all the other papers use this, use this notation, except the one of the survey paper, which tries to change the notation. And, but I don't think necessarily people follow the survey paper. Okay. Sounds good. And I think actually just for notational, so people, if you write most of the paper or the tutorials, they would just write epsilon here. But I think it's more proper to actually have a way to differentiate different epsilons at different time, because this epsilon means different things for different t, little t. So because this is literally equals to this, right? This, so I think I would just write it like this, because I think that will simplify, make it clearer. And also note that this epsilon hat t is, right, is basically this random variable, the sum of independent Gaussians. So epsilon hat t are not independent with each other, even though epsilons are independent with each other. However, you realize that, every time we talk about epsilon hat t, we don't really care about they are independent or not. So whether it's independent or not, it doesn't really matter. Yeah. Okay. Great. So, and now I think the most important thing that we read from this is that if you look at, so xt is equals to some scalar times x0 plus some Gaussian random variable, right? And this scalar, so alpha bar t, will converge to 0 as t goes to infinity, because you are taking product of many numbers that are less than 1. And eventually, even if each of them is just a slightly less than 1, maybe 1 minus 1 e minus 2, then eventually this will converge to, the product will converge to 0, actually relatively quickly. So, and that means that when alpha bar t converges to 0, then xt, which is equals to square root alpha bar t x0 plus this. I'm just rewrite it. This will converge to just the standard normal, because this will converge to 1, this will converge to 0, this will converge to just the standard normal distribution. So basically xt, when t is big enough, will be more like a Gaussian distribution. So, or maybe I think actually in some sense, if you really want to formally write this, is kind of like the distribution of xt given x0 will converge to not only just the marginal distribution of xt, but actually the conditional distribution of xt given any x0 will be converging to standard normal distribution as t goes to infinity. By the way, many of this convergence stuff is kind of like written in a relatively informal way. I think if you really want to formalize everything, you have to check all the regularity conditions that define what convergence you mean, so on and so forth. Yeah. And so basically, from now on, we're going to assume that xt is really just a standard normal Gaussian. because of this, because we're going to choose large T and X capital T, whether it's conditioning on X0 or not, will just be standard normal, Gaussian. Standard normal distribution, yeah. So
you said it's also, but it's not IID, it's like the epsilon there is not.
this epsilon hat T, right?
Yeah, but this is just like one epsilon, it's not IID.
So now the IID with each other, like epsilon hat T and epsilon hat T plus 1, epsilon hat T minus 1, all of these sequence of random variables, they are not IID. So they are not independent with each other. They are all, their distribution is always, their marginal distribution is always not normal, right? But they are correlated with each other. They are sums of, of this. It's kind of like if you think about it, they're actually like a nearby, like a epsilon T and epsilon T minus 1 actually are very close. Yeah.
I see that the epsilon T turned into like localized alpha because it's like the sum of all these functions like the summation expression to the one plus.
So you are saying that why this is equal to this? Is that the question? Yeah. So I didn't derive that. I think you can try to do a telescoping sum just by looking at the sum of the squares of the standard deviation here. It will be equals to this. That's by telescoping sum. Another better way is to just, I think I say it in verbally, so maybe I'll just try to formalize. Another way to write it is that as a fact that if x0, the covariance of x0 is identity, then the covariance of xt is also identity, right? You know this as a fact because I derived this, right? So, and then let's say you don't know what this number is, right? And you know that, but if you just plug in, you just say this is a question mark, right? You say xt is equals to square root alpha bar t x0 plus a question mark, let's say, whatever, like let's say, theta, what's the right number for, let's say, kappa times epsilon high t, and you know what kappa is, but you know this thing, you can say covariance of xt is equals to alpha bar t times covariance of x0 plus kappa square times 1 identity. And then you know this is identity, you know this is identity, you can solve what kappa square is. So, right, you just have identity is equals to alpha bar identity plus kappa square identity. So kappa square has to be equals to 1 minus alpha bar t. So in some sense, yeah. Okay, any other questions? Okay, so maybe one comment here is that this so-called forward process, this process from x0 to xt, this noising process, which is often called forward process, is a fixed process, like there's no learning involved at all. This is what we design, right? Like we know what the beta are, we know the process, so you can run it. There's no any uncertainty, like no learning whatsoever, right? You just design it, yourself. So basically the forward process is known. And that's, I know we didn't teach the VAE, the variational autoencoder stuff. This is one of the big difference between this and some of this variational autoencoder. Just in case you are familiar a little bit with those, like in variational autoencoder, this forward process is also a neural network, which you have to learn. And the other process is also what you have to learn the pairs. And here, one of the big differences is this direction, no learning whatsoever is designed, and you just learn the backward. So, and now we're going to learn the backward. So before learning the backward, we have to parameterize the distribution that going back. So basically, okay. So the first thing to realize is that, now we're talking about reverse process, right? The reverse process, which will be, the reverse process, fundamentally, you can just, you don't have to do anything. You just say qxt minus 1 given xt is the reverse process, right? You just, this process exists, but you don't know, right? And also maybe here when I'm writing this, I'm already using a fact that the reverse process is also a Markov chain. So I think this is a fundamental fact about Markov chain. If when one direction is Markov chain, the other direction is still Markov chain. So basically, xt minus 1 given and xt are independent if you see xt minus 1. So basically, in a reverse process, if you know the true Q, if you know this quantity, then you can just keep sampling from this quantity to revert it. So, but the problem is you don't know this. This is unknown, right? In some sense, this is the unknown ground truth reverse process that you want to recover to some degree. And we'll try to recover it, right? But we need to first parameterize it. So how do you parameterize? So the parameterization is that you're going to use a model P theta, which is also a Markov chain, right? So basically this model, given xt, it generates the distribution of xt minus 1. So, and it's a network parameterized by theta, and the type signature is that given xt, it will generate a distribution of xt minus 1. And this distribution is actually gonna be like just a normal distribution of this form. This is our choice. We choose this distribution to be a normal distribution, and the mean is a function of xt and t, and the variance is something like sigma t squared. By the way, here we are using the variance with a squared number. So this is my parameterization of this distribution. So this is a network. Given xt and t, you're going to predict a single scalar, not a scalar, a vector, because everything is a vector. And then you have a variable sigma t, which is what you choose as the variance. I think you can even learn sigma t, but for this lecture, we just say sigma t is chosen, and actually you'll see what is the right choice of sigma t, or what is one reasonable choice for sigma t. So sigma t is not something you're going to learn. Theta is something that you're going to learn. And this mu theta is a neural network. So basically, we need to design a loss function to learn this neural network. So,
Sorry, the forward process,
okay. So this is the forward process. Yeah. Mm-hmm. So.
Oh, so when you say reverse process, I'm referring to P.
I'm referring to Q. So like give me a noisy thing, how do you reconstruct a clean image, right? How do you reconstruct a cleaner and cleaner image? Yes, yeah. So I'm talking about the reverse of the noising process, the denoising process. But, maybe pay attention to the index here. So this is t minus 1 given t, which is, wait, did I write something wrong here? No, yeah. So the forward process is that, so the forward is qt xt given xt minus 1. Right? You use a smaller index to get to a larger index. That's the noising process. And the reverse process is given a noisier image, and you try to denoise it. Yeah. So basically all the reverse thing is have this type signature that you are given an image that is with a bigger index, and you are trying to reconstruct an image with smaller index, which is supposed to be cleaner.
One question about the noising process. I mean, why didn't we just take, like, at the end, if we have a Gaussian from like 0, I distribution, like xt/x0, that's what we wanted at the end. Why are we doing this entire Markov chain? Why don't we just like have a xt/x get from a normal distribution?
Yeah. So why you don't just do it one step, right? Because you know a formula that can do it one shot, right? So, and the one shot is just in some sense, the one shot formula is just you get rid of the x0. You just multiply x0 by 0 and then add a Gaussian noise, right? So I think that's one of the beauty here, because then it's going to be harder to reverse even, right? Because you lose. So this is giving you some kind of like gradual approach to try to reverse step by step. So in some sense, there's some benefits that is from the learning perspective. Like if you are noising step by step, then the denoising can also be step by step, and that's beneficial. Yeah. And in the another alternative, which is some kind of like in the middle between your version and this version, is that you not do it one shot, just multiplying 0 with x0 and plus noise. You can also do it with a neural network with 5 layers, 10 layers, something like that. And the story or the belief was that, if you do like for 10 layers of networks, then each layer will add some more noise and maybe remove some of the unnecessary information to make it kind of more like a Gaussian. So that's the variational autoencoder stuff, in some sense, right? But that is a learned network. So the difference here is that it's actually more brute force. Like you are just adding small noise every step. And the T is bigger here. It's like, the first paper was like 1,000 for T. Maybe a few thousands even.
Because we want to actually learn like denoising step by step instead of denoising this entire big thing, which is going to be, I guess, harder.
Yes, I think that's the intuition. Yes. There are actually many explanations for why this is working. That's one of the intuition I believe is indeed true. Yeah. Cool. So this is my parameterization for the reverse process. So maybe one question you may realize is that why is a Gaussian? So why the reverse process, why you parameterize it as a Gaussian? A priori, it's not clear why this is Gaussian, right? Like, given you add Gaussian in one direction, why in the other direction you also add you also kind of add Gaussian? Of course, it's not purely adding noise. You are going to transform the mean. You're going to compute some mean, but then you add some noise back. So this is actually from a kind of like pretty deep theorem where, I think at the very beginning, I think even it's not Gaussian, you can try to parameterize in this way. Even it's not really Gaussian, you can try to learn it with a Gaussian distribution, or approximate with a Gaussian distribution. That's one possible justification. But actually, there's a deep reason, which is that, especially in the continuum limit, when T is very big and each of the steps is really, really small, I think the reverse process the true reverse process, which this one is also actually a Gaussian. So that's from, a theorem like from, stochastic process, which is like a pretty deep theorem. You can actually, I don't know which one is the first paper that proved it, but I think, there's you can even date back, it can even date back to like some paper in 1940. Let me see whether I should talk about that at this moment. I think, this is the first time I'm teaching this lecture, so I'm trying to see whether I should cover the details. But maybe I'll answer a question first.
Yeah, I was just wondering, like the parameterization formula looks very similar to the one for DAEs. I was just wondering if like diffusions may be like a series of events.
Yeah, it depends on how I interpret your your statement, right? Like you can always say yes, it sounds like a similar, but there are differences, right? The difference is probably more, it's why it's better, but not a similarity in some sense. Yeah. Because in some sense, if you think about it, like almost everything is like this. Like every time you want to learn distribution, it's always like Gaussian with some mean, which is a neural network, and variance often sometimes is also a neural network. Here, actually, the variance is not. So they all look somewhat similar. The difference is probably what's more important.
I understand it. Like the reason DAE isn't quite optimal is because the difference between like the LMO and your true distribution is you can never minimize like the KL divergence because the covariance matrix you're using for the normal is like diagonal. Is that what diffusion is solving here? You're not using that approximation.
My final thing is also diagonal covariance.
That's not what it is.
It makes the steps smaller and smaller, right? So like you are, when you have I think in my opinion, the real thing is that you stretch the timeline to very, very long. At least, that's the original paper. Eventually people actually find out how to do the reverse process even with like 4 steps. But it's kind of like you always have to learn with more steps and then try to make it faster. So that's a separate story. But generally speaking, when you have a longer time horizon, each of these becomes easier to reconstruct. I think that's probably the main thing, right? So that, maybe you can say that actually when you say easier to reconstruct, actually, you can interpret that as it's easier to minimize your elbow, or maybe your elbow approximation is more accurate. So there are different interpretations of the same statement.
We notice something like adding Gaussian, but then to reverse that, we're still adding like variance, right? Isn't that like a violation or something?
Let me talk about that in a moment. Yeah. I think it's I understand your question, but I can answer that. Yeah. Okay, so maybe let's talk about that. I think, So why the reverse process still adding Gaussian? So let me see whether I should, give so in some sense, if you think about the Brownian motion, so it's how many have you heard of like Brownian motion or some kind of like this? Okay, great. Oh, that's fantastic. So I think, if you have a one-dimensional case and you're just adding some noise each time, right? Something like this, right? So, in the forward process, you are adding noise each time. So you get a bigger and bigger variance, in some sense. Of course, I'm only drawing one trajectory. Maybe the other trajectory is like this. You never know, right? This sounds like too aggressive. You cannot change that. But anyway, something like this. What happens is that if you give me this point, let's say this is xt, can you really recover the point before, the xt minus 1? You cannot really know, right? Exactly. So there's still uncertainties. Even given xt, you don't really know what xt minus 1 is. Because given xt, you may say, oh, maybe the previous point is here. So that's how you got here, right? But it could be that you got to xt from a different trajectory. It could be like you are going this way and then go here. So basically, even given xt, you don't know what happens before, right? So that answers the question about why there's still noise, because you never know how you got here. So that's why there's always a noise. This is always a distribution. And that's the second question is why it's Gaussian, right? So Gaussian is, I think the Gaussian entity is interesting in the sense that, so in some sense, for most of this, so if you go to the continuous time, almost every stochastic process is Gaussian. Like there are special cases where you have to design something, but generally speaking, the reason is that in some sense by law of large number, right? If every small step you add some noise. Let's say that noise is not really Gaussian, something like Gaussian. Once you have so many steps, then you accumulate to Gaussian. Right? So in some sense, like it's always kind of Gaussian in some sense. Like, once you have and you can, and there's no so-called small enough steps, right? Like your small step at this moment it could be accumulation of even smaller steps. So any step, is accumulation of even smaller steps. And if you have enough accumulation, you always get to a Gaussian distribution. This is not always true. There are counterexamples here. That's why stochastic process is interesting. But in most of the normal regular situations, everything is Gaussian. So the forward and reverse is always Gaussian. So, and actually that's kind of like what I'm trying to state here. This is, it's a pretty deep theorem. Maybe, so maybe let me just, have a small distraction to talk about the continuous perspective. I kind of like to talk about this because in some sense, this is one of the area of machine learning where you can actually talk about some of the math. Once you go to large language models, it's kind of like you just, you write down 3 equations and you are done. Okay, anyway, so how do you think about a continuous perspective? So I don't expect everyone to know all the kind of notations here. I don't necessarily understand all the formal definitions, to be honest. So I think we'll stay informal to some degree. So when you have a continuous time, then how do you write this kind of like forward process? What you do is you write something like this. You do say dxt is something like, you have a deterministic drift dt plus this Gaussian noise. So this is the so-called Brownian motion. And this is the variance, which is kind of like that the beta t, or square root beta t. GT is the square root beta t, yes. And this is the Brownian motion. And this is the deterministic change, which corresponds to the difference between this and this, right? So that's the difference between the two steps deterministically, and there's a stochastic part. So basically, this is the deterministic case. And on the left-hand side is basically, this thing is kind of like the same as xt plus 1 minus xt, more or less, you know. Here I have one step, but like if the step is really small, or maybe I should say t plus dt minus xt plus dt minus xt, something like this. This is the change in one step, and there are two parts. One part is a deterministic change, and there's a stochastic change. So that's how you kind of like model this in a continuous language, and I think there is a result. I don't think this is necessarily the first result, but I think it's a convenient set. I think this is Anderson 1985. And it's saying the following. It says that if you, I guess there are also different ways to state the results. I'm using a somewhat kind of like from the notation perspective, it's not the most clean one, but I think it's easier to understand to some degree. So basically, let's say, suppose you have this, okay, so you have a forward process like maybe x0, you know, so on and so forth up to xt, and then you can define a reverse process, which is let's call this y0, and this is yt, and so basically y, and this way, so y tau is equals to xt minus tau. That's my definition of y. I change the order and change the time direction, so that's my y. So I think this Anderson et al. Says that if this is the forward process, then the backward, so if you look at the stochastic process for dy tau, then is equals to this. By the way, you don't necessarily have to note down all the details here. It's all in the lecture notes, with probably fewer typos. I think the lecture notes, I checked it relatively carefully. So yeah, okay. So basically the reverse process, if you're indexing by tau, is like this. So this part is the deterministic part, and this part is the stochastic part. And you can see the stochastic part is still adding Gaussians. But the deterministic part is kind of more complicated because you have to kind of like take into account that how did you kind of generate it in the first time in some sense. And there's this part about the density because you have to incorporate in some sense it's kind of like here to understand how you go back. You have to understand a little bit about it. How you go back from here versus how you go back from here is different, right? Because if you're here, the most likely your xt minus 1 is kind of like lower because it's less likely to arrive here this way. It's more likely you are arrive at this high point through below as opposed to through above. So that's why your distribution will be more likely, the mean of your previous point will likely drift downward if your xt is really high. But if your xt is kind of like low or maybe in the middle, then it should be symmetric in some sense.
On the third line?
The W bar. The W bar is just the Gaussian, like the Brownian motion, in the reverse direction. It's just that you use a different notation to indicate it. And actually, I think yeah. Okay, sounds good. And this term is just literally the same as this. It's just in a different direction because just now you are reverting the direction. So in some sense, these two terms are the same, and this term is what actually matters in some sense. Like yeah. Let's see. I even have some derivations for why this is true. But I think maybe,
Quick thing. So about like learning that mu in there, that is going to be learned. Is that how do you learn that? Like
we haven't talked about that at all yet.
Okay.
So maybe one thing here is that why I brought this up is to justify that this is a Gaussian, right? Because the reverse process in a continuous thing is a Gaussian distribution. So that's why it makes sense in a discrete case you parameterize it by a Gaussian. That's pretty much the only thing I'm trying to say. I think I'll skip the derivation for this. In the lecture notes, actually, I did spend some time to try to give an intuitive proof for this. So in some sense, it's kind of like the general approach is that you are using Bayesian rules with a lot of like Taylor expansion. I think if you're interested, you can read the lecture notes. So now let's talk about training, how to train these models, right? So you can forget about continuous case. This is what we commit to. This is my backward process. I need to design loss functions for training this p theta. And another thing I want to, I guess maybe before going into that, I think I realized that I'm not sure how many of you kind of like are confused by some of these notations in machine learning. Like, for example, when I write this, nobody seems to complain with me about the interpretation of this equation. So, if you're a mathematician, you're probably not happy because the right-hand side is the distribution. And the left-hand side is, it depends on how you interpret it. So typically this is kind of like the conditional density of xt minus for given xt is a scalar. But this is very kind of like common in machine learning. People kind of like just, so first of all, like, the variable, this notation xt, there are two meanings here. One meaning is the random variable xt. And another meaning is a particular choice, is a numerical number that this random variable is taking in certain cases, right? So I think that's very commonly accepted. So you have two notions of this. And then there's this thing, right, which is even more confusing because this can be either a scalar or a distribution. So, I think, some people try to, make this less ambiguous by saying that you can write this. So actually this is the notation I use in the lecture notes. So you can write this as this. So xt So, and what is this one? This is the Gaussian density, which is the density function, something like, this is exponential 1/2, like you say, nx comma mu sigma square is defined to be this scalar, which is 2 pi sigma square root, this exponential x minus mu square over 2 sigma square. So basically, now you make the right-hand side and left-hand side are both functions or densities, right? They are functions. This is xt minus 1. So they are both functions in xt minus 1. Minus 1 is kind of like a variable. This is a function. This is a function. Or maybe if you plug in the numerical numbers, they are both scalars and they are equal. So, and, or you can probably say that there's maybe the law, under p theta xt minus 1 given xt is equals to this distribution mu theta xt t. So that's another way to write it. You just say this is this conditional distribution and this is the conditional distribution. This is a distribution. Both left hand side, right hand side are both distributions. Yeah, but most likely even you just write this blue line, you'll be fine in any papers.
Is it common to use a lowercase letter to denote the particular value and a capital letter to denote the random variable? Or is it just one of those?
No, it's in this area. No, like you don't have to use capital letters and and it doesn't actually help that much in some sense. If you really try to write it, in many cases, I don't think it. Anyway, so people don't distinguish them. People just always use small letters. I guess you can see like here, I'm using actually the capital letters for the random variables, because that's, in the mathematical literature, you see these differences, but in machine learning, no. Yeah. Okay. So, okay. So that's, some clarification of notations, but I think, you will see this many times. So it's good to understand what this means, but it's not kind of like that. It's a little bit ambiguous. Anyway. Okay. So now in the next 20 minutes, I think let's talk about how to learn, the diffusion models. Probably we won't able to finish it exactly, but that's okay. So how do you learn this? You use this, the general approach is still this kind of like a EM algorithms, or the elbow, the evidence lower bound or variational lower bounds, whatever you call it, they're the same thing. So basically you want to do maximum likelihood, but you have some hidden variables and you cannot do that, so you have to use the evidence lower bound, and you derive the evidence, the elbow lower bound, and then you try to optimize the lower bound. So that's the general approach. So let's try to go through it. There's some nuances on how do you actually apply the methodology. So your goal is to maximize log p theta of x0, right? So by the way, p theta of x0 is basically the marginal distribution of x0 under this whole p theta thing, like this, because this p theta defines a process, right? P theta defines a process, which means it defines a joint distribution over all the variables x0 up to xt, and and also it defines a marginal distribution over x0, right? So this means the marginal distribution of x0 under that process defined by p theta. So you want to maximize this, and you have under the hood you have a disjoint distribution x0 to xt, right? So I think the way to do this is that you treat xt, and you treat this as the latent variable z in the elbow that Chris talked about, and you treat this as the same as x. So in some sense, if you all of this as z and all of this as x, and then you can apply the lower bound in some sense. And by the way, so maybe let me try to remind ourselves like what's the elbow we have talked about. I think the elbow we have talked about is that the log of p x, say theta, is larger than, I think, expectation under some distribution q, say the log of p x given z minus KL between q and p, the distribution of z. I think this is the notation we used in the previous lectures, right? So like you have some kind of like posterior q, which is to estimate z given x, and you first sample it from this posterior, and you look at the reconstruction loss, and this minus the KL divergence between the prior PZ and the posterior Q. Okay, so that's the elbow lower bound that one of the versions of the elbow lower bound, and there are several different equivalent versions. So we're going to use this. So what is the Q we're going to apply? So let's see. So the QZ in the previous lecture notes corresponds to here, for our case is the Q x1 to t given x0, because you can see like z is my x1 up to xt is my z. So QZ is the posterior where you try to infer the latent variable. So that's why it's about given the x0, how do you infer the latent variable? That's why this is my correspondence. I'm trying to apply what we have learned last time to this case. So that's why I'm kind of making a correspondence between the variables. So, right. So this is my QZ. And the reason why we didn't write QZ given X is because last time the X is kind of like a fixed variable. So in some sense, you should even write QZ given X in the previous lecture. But just in that, last lecture, the X is kind of like fixed in that context. So, right. So, and this is, okay. So now let's try to apply this thing. I know this kind of like correspondence to our log px, p theta x, x0. So for us, log p theta x0 is bigger than, I guess, depending on how much details you want to see, but like, the first step, I think we can probably just directly apply this, if you believe in this, this is in the lecture notes. So this is larger than expectation of the reconstruction loss, which is a p theta. What is x? X is x0. What is z is x1 up to xt minus the KL. So the KL between what? Q is this, posterior of Q given, x1 to t x0. So this is Q x1 to t given x0. And this pz is the distribution of x1 up to xt, right? So this is p theta, x1 to t. By the way, here, in some sense, this is interpreted as a distribution as opposed to a scalar. Just to, I think in the lecture notes, I'm using the more formal notation, but here, I just use the informal version. This is a distribution of x1 to t given x0. This is a distribution of x1 to t and the p theta. And you are looking at the KL divergence between the two distributions. Any questions so far? I see some confusions, but I'm not sure which part is confusing. I guess.
Define the difference between Q and P.
The differences between Q and P. Q is Q is this process. Q is this, how do I say this? Like, Q is the ground truth drawn distribution, right? So you have, I guess you understand the Q, the forward Q, right? So this forward process of Q defines the drawn distribution between x0 and xt, right? So basically for every trajectory, you have a density, you have a number. So you have a distribution over the trajectories. So, and it's kind of like if you have a multivariable kind of like distribution over x1 up to xt. And then you can look at all the conditionals, under this drawn distribution, right? You can look at, maybe xt minus 1 given xt, you can look at any of the conditionals, right? So once you have a drawn distribution. So that's Q. So every time I say, x1 to t given x0, that means that you look at the drawn distribution and you say, oh, I'm looking at the conditionals under that drawn distribution. Does it make sense? Yeah. So, and p theta, is this, artificial one I defined in this way. So it also induces a drawn distribution. Because once you give me theta, I'm going to give you a drawn distribution over x1 up to xt. Right? And then you can look at, any conditionals, whatever you want, right? Like under that drawn distribution. So and everything there is defined as p theta. Any other questions?
So the scale evidence term is like, so you're using both the noising process as the posterior and the denoising process as the prior. I'm kind of a bit confused by that. Like, why are we using those Poisson distributions? Because I mean, like a prior is basically what you thought about the probabilities imposing the data, and the posterior is something you learned later, but then it seems to be like worse here.
Yes, yeah, I think that's it. So that's intentional, yes. So in some sense, it's kind of like yeah, I think that's the case. Just before both of these are parametrized, and now you just make one of them not parametrized. like in VAE, we didn't teach it, I don't know, but like in VAE, you see everything is parameterized by something. This is theta, this is phi. So, but now just some part of it becomes a fixed process. And maybe another way to think about it is that this formula, and our previous kind of lecture, this formula Q is the posterior, right?
Yeah, exactly.
So, but this formula works for anything. It's just any distribution. It's just inequality. So it doesn't matter what's the interpretation of Q or not, right? That's the, so we are using it, right? Like the formula is a generic formula. Whatever P and Q you put in is always correct. Yeah.
Could you explain intuitively why you subtract KL divergence?
No, this is, I'm just citing a formula from last time. So, so I guess you are asking why in the lower bound there is a minus KL divergence. I think, I'm not sure whether it's an intuitive explanation, but it's a sanity check, right? So if you don't have the KL divergence, then I think you can just choose, you can easily have perfect reconstruction. You just let Z to be the same as X. You don't even kind of like, doing any kind of like a posterior estimate. You just say Z is equal to X, then you have perfect reconstruction. It's kind of like you are lacking regularization, like in some sense, right? I think actually in the elbow literature, this is kind of like viewed as a regularization term. Like you cannot make your posterior, too complex, right? Your posterior has to be close to the prior, otherwise it's just you are overfitting to your data in some sense. Does it make some sense? Yeah. So, okay, cool. So that's by the way, this is I've never seen people deriving this, there's still 1 or 2 steps, below. But this is my, simplification of the derivations. All the materials I've seen is kind of like, you just start with the lower bound and you just do kind of like a 1-page derivation and, and you get some formula and that's it. So at least I think we are introducing a little bit of structure here, hopefully. At least it makes the proof shorter. So, okay, so what's the next step? So next step is that this is, 2 distributions, these are both distributions over the trajectory from 1 to t. And you can use this so-called chain rule for KL to decompose. So, let me see where I should write it. Maybe just, start from here. So there's this fact about KL, which is like, so this is the chain rule for KL, which is that if you have KL between, let me see what's the right way to write this, let me think about what's the more abstractive way to write this, if you have P, let's say, of XY, I'm writing an abstractive statement, right? So you have two, this this multivariate random variable, X and Y, and you have 2 distributions, and you look at the KL between them. This is equals to KL between, P of X given Y and Q of X given Y, plus the KL between P of X and Q of X. Oh, sorry, Y. Oh. And similarly, if you have KL between a sequence something like this, x1 up to xt, q x1 up to xt, and let's say, suppose x1 up to xt is a Markov chain, and both p and q, and then you can do this chain rule where you can write it as p of x1 given x2, Q so you have this you can decompose it sequentially, and the last term will be just the xt. Yeah. So that's the fact that we're going to use for this chain rule, so that we can decompose that formula. So and this is a very basic formula for KL distribution. I guess this one you just verify it by expanding the definition, and this one you can use it. You can use this formula to derive this one just recursively. So now you can see that I'm going to apply this to this distribution, this KL. So now the KL between P of x1 to t given x0. Sorry, did I have Q first? I have Q first, yes. Q. This is equals to right, I think so this whole thing corresponds to this thing, right? So like so x0 just assume that it's always there, and this p corresponds to this one. So and you decompose it this way. So that's why each of these KL is only about one step. So before you have a KL between two joint distributions, and now you have KL, a sum of KL, and each of these KL is between it's between distributions for one step. And if you really try to interpret this, you can see that this is kind of like the reconstruction, because you are trying to make, it's actually kind of interesting. You are trying to make the one-step reconstruction to be the same as the reconstruction of Q, but a condition on x0. So basically, the kind of the magic here is that this term is actually easy, because given x0, you actually know what is the reconstruction of x minus 1. Actually, deterministically, like you can write down, you can compute a formula, right? So without x0, it's very hard to reconstruct. But with x0, it's actually easy to reconstruct. So basically, you're saying that it suffices for me to match my reconstruction to the reconstruction when x0 is given. Of course, you also have this term as well. It's not like only KL, but there are other terms. But here, at least, you're only asking the p theta to reconstruct xt minus 1. You want this distribution to match this distribution, and this Q distribution is conditional x0, which is actually a very easy one, which you can compute very easily. So I think I will try to, let's see whether, okay, I think 3 minutes probably is enough to get the rest of it. So let's just be a little more precise. So what is this one? So we know very precisely. So we know almost everything about Q if you condition x0 pretty much. So basically, you know Q of xt given xt minus 1 and x0. And this is enough to get you Q of xt minus 1 given xt and x0. So if you know x0, you know xt minus 1, you know what's the distribution of xt, right? That's because the forward process is quite simple, right? So if you know x0, you know xt minus 1, and you can add noise to get xt. So, and that's why the reconstruction of this is easy, because if you know, it's kind of like if you know, for any Gaussian distribution, right? If you know P of A given B, and you know P of A comma B, then it's easy to compute what is P of B given A for Gaussians. It's kind of like you have deterministic formulas for this. So that's kind of the situation, right? A is this, so everything is condition x0, and A is xt, and B is xt minus 1. So, you know everything pretty much. So, I think probably I'm not gonna do all the full derivation, but you can compute. So, just, if you do the calculation, you have xt given, xt minus 2 given xt and x0, you can do the Bayesian rule, which is xt given xt minus 1 x0 times q of xt minus 1 given x0 and q of xt given x0. And you see, you know everything here, right? What is xt minus 1 given x0? That's known because I have my, oh, did I erase that? So I think, remember, I know xt is equals to square root bar x0 plus 1 minus square root alpha t bar epsilon high t. So I know the relationship between xt and x0 very well, so that I know the distribution here. And I know the distribution here because actually here is even easier because you don't even have to condition x0, it's a Markov, so you can remove x0. So you know xt given xt minus 1. And you know this one for the same reason, because you know the relationship between xt and x0 exactly. Because it's Markov, right? So given xt minus 1, you don't even need x0. Yeah. So basically all of these quantities here are known, and you can just plug in, there are probably, there are actually, in the lecture notes, we have a slightly faster way to do it, but in principle, you can plug in all the density functions and you can just get the formula. So basically, eventually you can compute this, and let's say we scale a lot of steps. Eventually, this is just Gaussian distribution, with, something like, I'm trying to pay attention to time, sorry. So this is Gaussian distribution with, it's a complex formula. Square root alpha t bar. I don't think you can verify this. I didn't verify it myself, strictly speaking. So x0 plus square root alpha t 1 minus alpha t bar. So it's a distribution that is, where the mean is a linear combination of x0 and xt. That's the most important thing. The coefficients, I can never remember it. But some linear combination of x0 and xt, and the variance is some function of alpha and beta. So, and people often just denote this to be mu tilde t xt x0. But actually, it's just this is just definition, right? Mu tilde xt x0 is just a linear combination of them with some specific coefficients. And so that's why this distribution is just literally a Gaussian, and this distribution is literally Gaussian, and you know the mean and variance of all of them. So basically, we are computing, for this term, we are computing the distribution of this Gaussian versus what is the P. P is this one. So basically, imagine you are taking the KL between this one and this one, right? And but you know all the formulas, so you can code up the formulas too, because you know the distributions, mean and variance. It's a very complex formula, but you can do it. Maybe just let me spend 1 minute to write down what's the actual. Maybe just let me write down here. Where is it? So if I define this term, as LT minus 1. I think that's how people define it. So LT minus 1 is just a KL between two Gaussians. And one of this Gaussian is this one. And one of the Gaussian is this Gaussian, right? And there's actually a formula for that because, I think maybe one small thing is that actually what people choose is that at least one option is you can choose sigma squared to be equals to that number. So that these two Gaussians have the same covariance. Maybe let me just mark down the two Gaussians here. This Gaussian, the two orange Gaussian, what's the KL divergence between them? So if you choose the variance to be the same, you choose sigma t squared to be equals to that number, then they actually have the same covariance, and the only difference is the mean. And actually, you know that if you have two Gaussians, with the same, so abstractly speaking, if you have two Gaussians with different mean but same covariance, maybe it's the same mu and mu tilde, sigma square identity, then this is equals to something like, maybe let's write sigma. This is equals to mu minus mu tilde with this. And this is just the mu minus mu tilde transpose sigma inverse mu minus mu tilde. So it's a quadratic form of the difference of the means. So, and in this particular case, if you plug in all of these numbers, you get just the difference between the means, right? Like you see, like here, the abstract speaking, you are looking mostly at the difference between the means. So I guess the difference between the means is this mu theta versus this mu tilde. So you get mu theta xt t minus mu tilde xt x0 square. And with some coefficient, I think the coefficient is 1 over 2 beta t tilde. So that's the formula. So now you have a very concrete formula for the loss function, which is a function of theta, and you can minimize this loss function, or maximize actually. You are minimize this because there is a minus sign in front of the KL somewhere, and you're maximizing the lower bound. Okay, so I think I'm already 5 minutes over time. I think there's a little bit kind of like a simplification for this, which we'll cover next time, but this is the gist.